All right, let's get started on the next session. I will do this slightly differently by introducing our distinguished guest speaker first, and then I will tell you a little bit about the context before his talk. So I have the honor of introducing Professor John Martinis, who, for those of us who work in quantum science, needs no introduction. But if you work in other fields, I'll tell you a little bit briefly about his work. Professor Martinis got his Bachelor of Science in Physics in 1980, and soon after went to Berkeley, where he did his PhD work, working on some of the first experiments aiming to observe coherent quantum phenomena in macroscopic electrical circuits based on superconductors. These successful experiments created a lot of interest and a chain of activities that ultimately gave rise to the development of superconducting qubits, which are one of the leading platforms for quantum information processing today. In this exciting journey of developing qubits, Professor Martinis gave our community a lot of brilliant ideas and beautiful experiments, which really form a core part of our knowledge base for engineering and building these devices, but also equally importantly shapes our understanding of the foundational physics of these systems and how they interact with their environment. So he's a professor of physics at University of California at Santa Barbara, where he has been since 2004. During this time at UCSB, he also joined forces with the Google AI Quantum Lab, where he led one of the first industrial efforts on building a prototypical quantum machine. So he led a team of scientists and engineers that brought about technical advances that culminated in building a multi-qubit quantum processor that was reprogrammable with unprecedented levels of coherence, system size, and connectivity. And in 2009, this system was shown to be capable of running quantum algorithms with a level of complexity that for the very first time posed significant challenges for our conventional classical computers to replicate. So this milestone result of demonstrating quantum computational advantage, or also known as quantum supremacy, was recognized by the John Stuart Bell Prize, which Professor Martinis got in 2021. So I will briefly talk a little bit more about superconducting qubits and how the research in this area is related to nanoscience and technology before inviting John back to this podium. So, looking at a high level, we know quantum physics is about studying light and matter at the most fundamental level, where we have single quanta of energy. Superconducting qubits, however, are engineered artificial structures, which I'm sure we'll hear more about, that are made from many, many particles, and they are actually rather large. Interestingly, though, these devices are made such that at some sense they behave like fundamental particles, and they are able to preserve and manipulate quantum states, which is the reason they're very exciting for quantum information processing. The interest in utilizing these devices is partially motivated by the rapid improvement in the performance of these systems, which one metric for is this notion of lifetime or coherence time, which roughly tells us the duration of time that the qubit can preserve a quantum state before the interaction with the environment destroys that state. And as you see from this logarithmic scale, there has been a very rapid improvement in these systems over the past 20 years or so, which is quite exciting. But at the same time, one of the unique features of these systems is that they rely on microfabrication technology of the very type that we use for building semiconductor devices, which allows you to put a large number of these devices on a single chip and route wires to them and control them, which I believe is a topic that is quite related to the talk we will be hearing soon. So all of these makes these systems uniquely exciting for quantum information processing. But also, one of the key properties of these systems is their ability to talk or interface with other types of physical systems that also reside in solid-state devices. For example, a variety of processes can be used to map the state of a superconducting qubit, which typically operate at very cold temperatures in a cryostat, to an optical photon. And interestingly, optical photons can carry quantum state to room temperature without getting disturbed by our thermal environment. So this is an area that is actively pursued in Caltech. The groups of Professor Oscar Painter and Professor Andre Faraon have done a key experiment demonstrating these types of devices, which can essentially convert microwave quantum states to optical domain. And a wider community right now, including myself, are actively working on making these types of microwave to optical interconnects to attach superconducting qubits to optical communication networks, where the goal is to make larger systems where you can process quantum information at a larger scale, or do things like remotely accessing quantum computing clouds in the future if they become a reality. To provide another example of the degree of impact of these qubits and the way they interface with other systems, another notable examples are mechanical oscillators. Mechanical motion in solid-state systems can exhibit quantum behavior if a system is cooled down sufficiently. And interestingly, mechanical oscillators also interface with electrical circuits of the very similar type that are the foundation for superconducting qubits. This is also an area where Caltech has have a rich history, and some of the pioneering work in controlling the quantum properties of mechanical modes was done here in groups of Professor Michael Rukas and Professor Keith Schwab. More recently, with the advent of superconducting qubits, electromechanical systems are now being used to prepare quantum states of mechanical motion in arbitrary ways, which is very exciting because it provides a tool for studying mechanical systems. But at the same time, there is an open path right now to hybrid devices where we can combine mechanical systems with superconducting qubits, for example, to realize quantum memory elements, which could be potentially beneficial because of their small size and superior coherence compared to microwave devices that tend to be rather bulky. The main reason I put this image here, this is from some of the work in my group, is to give you an example of the type of devices we need to make. From the sizes here and some of the features, you can guess that for the research in this area, not only you need quantum physics, but you also need a lot of tools from nanotechnology and nanoscience, in which KNI Institute has been really a key driver of our work. So I hope this summary give you an idea of the depth and breadth of the impact of superconducting qubits. Without further ado, now I invite our distinguished lecturer or speaker to come and start his talk. Thank you.
Thank you for your very kind invitation. I'm really excited to come down to Caltech and talk to you today. And I'm going to talk about how the field is actually getting quite mature at this point, where there's a variety of experimental systems that can make pretty good quantum computers that have enough qubits to do something really interesting. We've shown that the qubits can be powerful. And really the next step is people to make them better, make the system bigger, find the algorithms to start doing something useful, or as they say, utility scale. At first, this is going to be for scientific problems, hopefully for a problem that you can't compute with the supercomputer, or at least it's hard to compute, you could check it. And then eventually we hope to get to business kind of applications, in which case I think the field will really take off, because then there'll be a lot more funding going in to really perfect these devices. So I will start with a discussion of general quantum computation and some of the key features you have to think about. Importance of qubit errors. I will focus on how we did a system test of this with quantum supremacy at Google. Then the most important slide is what are the 4 critical qubit metrics as we move forward. And then future steps in particular for a company that I'm just starting right now. So just very briefly about quantum algorithms, we're using the laws of quantum mechanics and kind of wave behavior of information to do more powerful computation, kind of in an exponentially powerful way using quantum mechanics. You just can't take any algorithm that would be on your cell phone or PC and speed it up with quantum computation. You have to choose particular algorithms that map to the quantum computation properly. The first one that started the field out was factoring numbers, which is the basis of RSA security protocol called the Shor algorithm. People have talked about how eventually we might be able to do this, but because of this, people are developing new encryption algorithms that doesn't depend on this, and it's very likely that people will have that fielded before we ever build a big enough quantum computer, so you don't have to worry about security. I think the natural application for a quantum computer is quantum chemistry, and here at the Kavli Institute, this is very interesting because there's a natural mapping of qubits to electron bonds and how quantum mechanics works. And this is, in fact, I think it was first pointed out by Feynman many years ago. Many technical applications, we have known algorithms. They're going to be useful and powerful. People understand how to do that mapping. The problem is it's complicated enough. You're going to need error correction, maybe 1 million qubits. So that's off in the future. In a more immediate need, people are thinking about the application of optimization and machine learning. I'm going to give the example of this traveling salesman problem, which is a common thing to say, but it's really not a good example because the traveling salesman problem has very good classical heuristic solutions that you're probably not going to beat. But it's those kind of optimization problems you might want to think about. There are algorithms with known speed up for quantum data, but it's not exactly sure exactly how you're going to use that for classical algorithms. But there's a huge market for this. Even if it's heuristic, even if it's a relatively small improvement, it's going to be very valuable commercially. So a lot of people are working on that. I'm an experimentalist, so I'm going to talk about the hardware systems that people are building, because that's a key part of doing this. And it's a vibrant and varied ecosystem, lots of different physical systems that are actually working pretty well right now. I'll get into that. And then many organizational approaches from large companies, startups, government labs, university, all trying to build up the technology and infrastructure for doing this. Now, I want to start with the importance of qubit errors because a quantum computer is fundamentally different in terms of errors than your classical computer. Now, let's just go back on the left here with classical computers or CMOS or even TTL, and you build some kind of gate structure. You have some inputs, you flow it through some hardware, you get some outputs. And the amount of complexity, the number of logic gates, basically goes as 1 over the error of making those logic gates. So in the 1960s, you could build integrated circuits with about 1,000 transistors. So you could build TTL circuits and test them and then build up a quantum computer. And then over the years, the technology got much better so that the error rate is now way below parts per billion, and you can build multi-billion transistor processors, and do that economically and use that. Quantum, it's a little bit simple. This is a circuit model where we have the different qubits. But now, instead of laying out in space, this is laid out in time, where over time you do different single qubit operations and maybe 2 qubit operations, and then just varying this over time according to some instruction set, you then do your computation and measure it at the end. So this is over time, this is over space, but the basic idea is the same. Now, the real issue is that when you use quantum mechanics are inherently, let's say, fragile, so that there's going to be errors in the system. And there's no way you can get around that directly with physical. You can error correct and get around it logically, but you can't get around it physically. And the number of operations you're going to do in this kind of circuit is the number of qubits W times the number of instruction sets, or depth, D. So you have W times D instructions, and you're going to be able to do something with enough depth that basically 1 over the error of the gate, or so kind of the memory time of the qubit divided by the gate time. Okay, now let's take W equal 100, which is kind of where people are thinking about right now. You take an error of 10 to the minus 2, which is kind of pretty good for these qubits, not at the best yet, but it's pretty good. And you plug in this number, and that means you can have a depth equal 1, or maybe a few. That means you can have, you know, just a couple instructions. You can't do very much with that, almost nothing, okay? So what you want to do is bring the errors down to, say, 10 to the minus 4, and then with 100, you can have 100 instructions, and then you can start running some interesting algorithms, very qualitatively, of course. But that's what you're trying to do here. So they limit applications. If the error is greater than a few percent, in fact, you can efficiently simulate them with a classical computer using some approximation algorithms. So there's no need to build a quantum computer. Once you get below to about 0.5% or so, you can do this quantum supremacy experiment, test the physics, do something complex. And then when you get below that to the 0.1 to 0.01%, then you can start possibly doing interesting things. There's 2 strategies. Just use the raw quantum computer and use near-term algorithms, maybe hundreds of qubits. You can do error correction and then build it up by scaling up a complicated system. But the whole point is whatever camp you're into in terms of what you're going to do, you're going to need the lower errors, okay? And of course, the difficulty is getting these low errors and scaling it up at the same time. And that's what people are working on very hard. So I'll just talk briefly about our quantum supremacy experiment done at Google. These are made with superconducting qubits, which are little microwave, nonlinear microwave oscillators. So this is built all on a chip with a connected architecture here that's forward compatible to error correction. You build that chip and you put it inside a dilution refrigerator. It's very low temperature, so it's mounted on a circuit board with microwave lines going up to room temperature. This is operated at very low temperatures. Just buy a dilution refrigerator, expensive, but you just buy it, such that the thermal energy KT is much less than the quantum energy of h bar times 5 gigahertz. And this is nice because 5 gigahertz, not too hard to do microwave engineering, even for physicists, okay? And then you take that top of the refrigerator and you do it a rack electronics. It kind of looks like a high energy physics experiment, and you control all this and you can calibrate it and get it to work. So the experiment I want to talk for the quantum supremacy is showing that it can be powerful, but it's also a system test that these things are working properly. You know, you can build transistors that work well, but it's only until you build a very complex processor like this and getting everything working together at the same time that you can build a computer. So you have to do careful system tests. And what we do is we use the quantum supremacy algorithm, which just checks a general purpose way we're going to use the quantum computer, and it checks it in a way where we know what the errors are. So what you basically do is you take your circuit and you generate random numbers. So there's randomly chosen gates here, but it's known to us. So it's a known random, and you basically generate random numbers here. Now, what's interesting is because this is a coherent quantum mechanical process, there's coherence in generating these random numbers at the end. And certain outputs of zeros and ones will be more likely than others. And it sensitively depends on exactly how you program this. And this is very much like laser speckle, which I show here. You put a laser beam through frosted glass that diffuses it out. In some directions, you get a coherent addition of the signals and it's bright. And in other directions, it's a subtraction of the signal and it's dim. And the same way, some of these outputs will have high probability and some will have low. That's sensitively dependent on what you're doing here. So basically, you run this through the quantum computer, and you're going to get the high probability states. And then you check that with the same circuit running through a classical computer, simulating the quantum mechanics, getting those probabilities. And then you check if the states you get here were the high probability states here. And when you use this formula here, where you take your measurements and you plug in the probabilities here, you get an answer of 1 if it's a perfect match, and 0 if you had any error at all. So if you made a compiler error or did something wrong in your experiment, you're going to get a 0 and you know about it. That's really good for an experiment to really be able to tune up the experiment. So this is system validation, and you learn the control system very well. So this was the data from the experiment. The circles, ours from the quantum computer, checked against a classical computer. And when you have 10 or 20 qubits, that can just be done with a laptop. 2 to the 10, 2 to the 20 is not very big. Then as you get bigger and bigger, 2 to the 35 gets really big, and 2 to the 50, which is the amount of computation you're doing, then requires a data center at the end. Now what I want to point out here, without spending too much time, is these red circles here. There's also a black line here, and this black line is the system validation. This is a prediction from what we expected it to be when we measured 1 qubit and measured 2 qubits connected together in the circuit, kind of an initial calibration. And we take that initial calibration, there are going to be errors in it, and we use a simple classical formula to predict basically what we get here. So the nice thing of this data, even though it goes down exponentially, you can only go so far, it's showing that our quantum computer is working as expected. And in fact, if you go into the decoherence physics, it's very interesting. This error rates only get computed in a classical probabilistic way, high school statistics. Whereas quantum mechanically, you have all this wave interferences and very complicated. And that really, this fact, you expected this from the theory, the fact that quantum mechanically you get these complicated solutions, but classically the errors are simple and classical, means you can build a complicated quantum computer. That's a very fortuitous situation that allows you to build this. For the experts, we have the same fidelity, whether we have them highly entangled or not. And then you were basically doing a computation on a huge parallel, what's called Hilbert space or computational space of 10 to the 16. And this is what you need to do to get a quantum computer to work properly. So the nice thing here is it shows that the quantum mechanics of the quantum computer is working as you expected. As you scale it up, there's no additional horrible things that go wrong, and it gives you a lot of confidence that we can proceed with this and start making more complicated computers and more complicated problems. I like cross-entropy benchmarking. I was really proud that people here at Caltech use the cross-entropy benchmarking for an atomic systems called Rydberg systems, where they have a very complicated Hamiltonian, much more complicated than what we did, many body interactions. Looking at the cross-entropy fidelity, they were able to characterize their system real well. So this whole idea of checking for system performance is really powerful, and I'm glad other people are doing that too. It's one of the reasons we developed it. Okay, so now what I want to do is talk a little bit about how we're going to get the quantum utility. This is the really important slide. So, let's go through this very carefully. Now, to build something useful like a computer, or even a classical computer, there's many, many metrics you have to get right at the same time. And there's probably hundreds or thousands of things you have to worry about to build this computer. And you know, if you look at the press reports, people often talk about, oh, how many qubits did you have? And previously I talked about errors being important. But I'm going to distill it down to 4 important metrics, which I think are some of the key ones in understanding this. So they're the qubit errors, the number of qubits, their connectivity, and their speed. So we've been talking about qubit errors. The hard one to do is connecting 2 qubits and can have them interact in a proper way. Typical numbers now are about 0.05 to 0.5%. They've actually gotten pretty good in the last 2 years, and that means people can do really interesting algorithms. And I would say, I think ion traps are doing probably the best right now, near 0.05%, which is quite impressive, and it really shows that, you know, we're working on the problem. I'm glad that this is getting better over time. People always talk about the number of qubits because that's easy to understand, and you know, how scalable something is, you know, and you want to kind of know if the errors increase with number. I'm going to say IBM has been talking about a 1,000 qubit machine. I think it's more of a demonstrator machine than I don't think the errors are too high and you can't really use all that, but it's a really interesting machine showing you can do it. Also, very recently, there's been papers on neutral atoms, these Rydberg states, and they've been able to make large systems, hundreds of qubits. It looks scalable to maybe 1,000 qubits. So this is looking very interesting too. So a lot of things are happening on these primary metrics. One also has to worry about an architecture and how to connect things up. Basically, you want to connect different qubits together. The more connectivity is, the better. So for superconductivity in the Google, it was 4 qubits. 1 qubit was connected to 4. And at IBM, it's less, 2.5 on average. And in atoms, it's generally all-to-all, okay? But all-to-all is nice for near-term applications. It's really not necessarily needed for long-term applications. Now, and it's not really not needed for that. Now, I want to point out that when you build your classical computer, you're not connecting all the transistors to all the other transistors. There's always an architecture to it. And this is a very difficult system engineering to talk about what to do. My particular view is you want to have something like a 4 connection, which is what we were doing at Google. Because if you connect it in a square grid and you want to do error correction, if one of your qubits drops out because there was a fab error, you can still recover and run the algorithm, okay? And you're tolerant to something like 1% dropouts, maybe a little bit more. Whereas, for example, if you go to 3 connection, this is latest results of Google theory, you're not tolerant to dropouts at all. So I'm not quite sure if this is going to be the way forward because you know, you have to be tolerant to those kind of engineering constraints. In fact, IBM is talking about 6 connections in some of their more advanced machines. And Atom seems to be okay. The real issue here that one has to think about is speed. Okay, and we all know speed is important for these kind of devices. And 1,000 times faster speed is 1,000 times faster answer, or if you're thinking about business, 1,000 times more profitable, of course, all else being equal. If you're dealing with an exponential speed up due to quantum computing, sure, the performance matters a lot, but speed also matters because we're dealing with factors of 1,000. So in superconducting qubits, it's 50, maybe 100 nanoseconds for some, and you can do all the gates in parallel, okay? For atoms, they're typically much slower, okay, about 100 microseconds. So this is probably the kind of speed you had in the ENIAC, okay, long time ago. So this is 2,000 times slower. Very typical of atoms. So for neutral atoms, it's nice. You can operate them in parallel, which is good. And it's about 2,000 times slower. What the heck? Stop that. Sorry about that. Do not disturb. Okay. Maybe it was new data and I should have answered it. That happened once. And in atoms, it's much slower. Now, neutrals can go in parallel. It can be about 2,000. It's 2,000 times slower. Now, the ions in nitrogen vacancies are very good, but there you have to do the 2-qubit gates in serially, and the gates in serial. So that gives you an extra factor of slowness that's maybe 100,000 times slower than the superconductors. So again, it all depends on many factors, but you kind of want to go fast. And by going fast, of course, it makes the control a lot more expensive and difficult. But in the end, we just have to proceed making things and see what's going to work well. But speed does matter. So because of that, okay, I do superconducting qubits. And why superconducting qubits? Good system performance, error scaling speed, good path to lower gate errors. This is the big thing we have to fix right now, is bring our 8 gate errors down to what, let's say, atoms are doing. And what's nice is we have long coherence time, 200 microseconds, sometimes even longer. We have to get there. And it's possible to make fast gates, 20 to 50 nanoseconds. That's what we did at Google, which had only a 15 microsecond time. So if we can combine these, then we're going to have a ratio of maybe 10,000 between this and this. And that is like comparing a 100 microsecond gate and ion trap to their 1 second coherence time. So it's the same kind of ratio. That's really good. Of course, it's faster is always better. Now, the difficulty here is, although people are fabricating for many years and people are designing things, fabrication is fairly well understood, but there's not necessarily a reliable prediction of errors when you scale up yet. And so that really has to be worked on. Qubits have a large size, which is easier wiring, but it's challenging to scale to 100,000 or million. We have some plans on possibly how to do that. So let's talk now a little bit in the last few minutes about how we're going to improve fabrication, okay? And basically, to do this, you have to have a really better understanding of system engineering and materials and fabrication. That, to me, is the key thing to do. Now, if you look at the field, IBM right now has excellent fabrication. Basically, all the field is trying to do is catch up with them because they're doing a really good job. They are holding their intellectual property on fabrication secret. That's fair enough, and we're all trying to figure that out. But I think we can maybe do it even better than what IBM is doing. Now, what I'm trying to do now is use a strategy of a clear understanding of this energy loss and really what's going on, and especially thinking about the fundamental mechanism of surface loss and amorphous insulators on all the surfaces, and understanding that. Now, what we've done recently is we've been working transmons, but we've kind of used what in the field would be thought of as the worst design, okay? So people generally think that tantalum metal is better than niobium metal, is better than aluminum metal, and sapphire substrates are better than silicon. That's the general consensus, and we're doing the worst there. We're going to flux tunable qubits. This is what we did for the quantum supremacy. When you do a single junction, things tend to be better. And when you do a differential qubit, it tends to radiate less. So we're doing all the wrong things. But in doing that, very recently, we've gotten an average coherence time of 200 microseconds, which is more or less what everyone else is getting by following, these kind of rules. So we're really excited that there's some new things to learn here. I also want to say something that's very curious about our field, is if you ever express results, you have to talk about your absolute best hero result, because that's what everyone is comparing. And it's a little bit lame. I don't think it's quite the right way to do things, to know what's really good, but that's what we do. And yeah, this number, in fact, in our lab, we're really good at cherry picking our data, the way that the qubit is made. So this number has gone up to 800, and I think we can be in 1 to 2 millisecond range in the next few weeks or month just by taking more data, okay? But that's not real, of course, okay? Don't want to do that. The real thing we're trying to do here is we have an idea what's going on. We understand the fabrication from an academic point of view, and we're starting a new company where we're going to do fab, which we think is going to be better than what you can do in kind of industrial prototyping fabs, semiconductor fabs. And we're going to shoot for better reliability, better scaling, and trying to leapfrog this performance using special tools. So for example, when you make a superconducting qubit, you have a metal electrode, and the oxides on the various surfaces limit this. The most important of which is between the metal and crystal. And what we've done working with a company is build qubits where this is a silicon wafer and this is aluminum on top of that. And this is done in an in situ process so that you have a perfect, crystalline match or no amorphous oxide match between the silicon and aluminum. And these are the individual atoms and rows of the two materials. And using modern machines, you're able to, make that really perfectly and reliably. And we need to continue with those kind of processes. For the experts in the room, here's our 730 microsecond decay of the qubit. Fits very well at one particular frequency. As you move the qubit to different frequencies, the T1 changes from the 2050 microsecond all the way up to our hero device here. And this is an integrated histogram showing that, kind of the average value here is around 200 microseconds. And the big spread here is we actually understand from theory, it makes sense. It's actually saying that things are going kind of as expected. And we just need to push this out some more. And this just shows what happens with various devices as we change the gap between the metal electrodes. Basically says as you make the gap bigger, the T1 times gets better, which is what you expect, and some various design changes in doing it. So we're really beginning to get a lot of data and understanding very carefully what's going on in these devices. So with that, let me conclude here. Basically, a wide number of technologies are building quantum computers right now. They're working well in this quantum supremacy experiment where we really tried to do the system metrology very carefully. The computers work as expected. There's no horrible physics going on as we scale up that prevent these from working. So we have to continue working on it. And then to do something useful, make a utility scale. We're kind of at a big gap between theory and experiment. We have to work on new algorithms to make it a little bit easier to do something useful. And then we're working on making the hardware better and better. And at some point, we hope this will meet, we hope, and then we'll really have an exciting new technology to solve important scientific and I hope eventually business problems. So with that, thank you very much, and I would love to have questions. Questions? Yes?
So you mentioned in comparing ions and superconducting qubits that ion gates are much slower.
Right.
Is that a fundamental thing, or is it just the state of the technology?
If I may paraphrase the question for the audience who might not have heard. The question, I believe, is about the ion qubits, which tend to be slower than the superconducting qubits, and whether the speed difference is something fundamental or not.
Yeah. Okay, so in the entrance, giving a simple statement there, I simplified things a little bit. It's possible to make the gates faster, for example, in the neutral atoms, but you're always having to move the atoms around. and the mechanical movement of them are about 100 microseconds. And of course, it's the slowest thing that matters. And if you don't move them, you'll be able to make it faster, but then you get rid of something that's really magical about that system. For the ion traps, that's generally the gate times of that. And again, you have to move them around. So yeah, those gate speeds are having to do a little bit with moving atoms too. But of course, you know, you have to consider everything. These are very rough numbers, of course. But I think that's going to be hard to get orders of magnitude on those numbers.
Hi, John. Thanks for the talk. I was wondering if you could talk about, from your experience with Google, what goes into the 2-qubit gate fidelity and those fractions of a percent as you approach 99.99% here. What are the technical aspects that you encountered that are causing problems to reach that less than 0.1% error?
The question is about the gate errors as you approach beyond 99.9% fidelity, and if you could comment on the technical issues that you might run into and how to potentially solve them in this regime of parameters.
So in that experiment, we were limited by the 15 microsecond T1 energy decay time. And building that experiment was very complicated. We had to get a lot of stuff to work. So that was good enough, and we just did the experiment. And it was very clear that we were limited by that error. So the very simple statement is, as we, let's say, extend that by an order of magnitude, which I tried to show you, I think people know how to do now. Of course, you have to build a system. The hope is you can do 10 times better, which would take you to 0.05%. Now, of course, you have to worry about other noise sources and other things, but I think the gates worked well enough and they were controllable enough. I'm pretty optimistic that you'll be able to improve those errors by a factor of 10. I mean, things look very controllable. You know how to calibrate. So it's hard to, get the long coherence time and put it together in a package with lots of qubits, but I think that's going to work. So that's what's very exciting about our field right now.
So I think you're running a little bit behind on time. So in the interest of time, if we can leave some of the questions maybe for the informal chats after the session.
Yeah, that'd be great.
Well, let's thank our speaker.
Thank you.